So in this session, we are going to study how to do filtering in MATLAB programs. That is what we want to study in this session. See, what we have studied so far is the function which is used for calculating the coefficients of the filter, and also we have studied the function which is used to plot the transfer function of the filter. Now in this session, what we want to do is to see how the actual filtering is done. So what is the function for that? Okay, so let us start. So filtering basically means what? So you have got the time domain relationship between the input, that is xn, and the output. And for the FIR filter, this is the equation that you have got between the output and the input for using various coefficients and the delayed input values. So you can of course write a program to implement this directly. In that case, yn is the filtered version of xn. So xn will have many frequency components, but by using this particular equation and using appropriate values of coefficients, your yn will select the required frequency components in the output. This equation, when you implement, that is what will happen. Okay. Now instead of writing the program ourselves, what we are going to do is to demonstrate how the function is available in the MATLAB and how we are going to use it. So the filter function which is available in the MATLAB is simple. Y is equal to filter, provide B coefficients, provide A coefficients. Now remember, A coefficients correspond to the coefficients which correspond to the delayed output terms. They are not present in the FIR filters. Therefore, now this particular function is a general function which is useful for FIR as well as IIR filters. So when we are using it for FIR, we will simply set A equal to 1 and then using the coefficients, use the filter function to generate the output. That is what you do. Okay. So in order to demonstrate the application of this function, we will first of all state the filtering problem and then see how to write the program for solving this problem. Alright, so let's define the problem first. Let's say we are required to generate x1, which we call as low frequency signal, and this is obtained by simply first generating a sine term with 50 Hz frequency and generating a sine term with 100 Hz frequency and then adding the two. So this added signal will form x1, which we call as the low frequency signal. Then we generate x2, which we call as the mid frequency signal, and that is above the low frequency signal. So its starting frequency is beyond 100 Hz. In this case, we are assuming that it is 300 Hz. So x2 is generated by generating one sine term having a frequency of 300 Hz, another sine term having a frequency of 600 Hz, and then you add the two and that will generate your x2. Finally, you generate x3, which you call as a high frequency signal, and its lowest frequency is above 600 Hz. So it starts from 800 and goes up to 1000 Hz. So this is how we have defined our various frequency bands. This is the low frequency band, this is the mid frequency band, and this is the high frequency band. And what we do in order to demonstrate the functioning of the filter function, we add all these signals and generate x, which is sum of all the three signals. So x will contain all the frequency components right from 50 Hz to 1000 Hz. And what we want to do is to extract a particular band of frequencies. So we might be interested in extracting low frequency band or mid frequency band or high frequency band. And in order to do this, you will have to use different kinds of filters. So you can use low pass filter, band pass filter, and high pass filter. That is what we want to demonstrate. So the problem states that write a program to generate and display all the signals, all these signals you have to generate, and extract the desired frequency range signal from X. Okay. While doing so, you have to choose the sampling frequency, and the sampling frequency we choose is 10 times the highest frequency. So in this case, the highest frequency is 1000 Hz. So we choose 10 times F max. So that is 10,000 samples per second. Okay. Now let us see, suppose we want to allow the low band of frequencies to go to the output, then we have to build a low pass filter. So you must choose appropriate cutoff frequency for the low pass filter. So how do you select? Now to understand this, look at X1 and X2 again. This is our low frequency signal. So the filter that we build, we want that it should allow 50 and 100 Hertz to pass through. In fact, any frequency between 50 and 100 Hertz, although in demo we have generated only 2 terms. So it should allow this low frequency band to go through, but it should stop the frequencies higher than 100 Hertz. Now the next frequency of interest in our signal comes from 300 Hertz. So we should choose a cutoff frequency which is lying somewhere between 100 and 300, so that the low frequency band is passed but the mid frequency and above is rejected. So for that we choose a cutoff frequency which is lying between 100 and 300, and let us say we choose it as 150 Hertz. So in that case, the coefficients B are found by the FIR1 filter which we discussed in the last section. 100, this is the order of the filter. WL, this is the normalized cutoff frequency, and low says that we want to generate coefficients for the low pass filter. So WL, recall that for FIR1 it is defined as 2F by Fs. So our F cutoff frequency is 150. So this is 2 into 150, 300 divided by Fs. Now suppose you want to extract the mid-band signal, then you need to change the coefficients. And how do you obtain them? So now since you want to reject X1 and you want to reject X3 but allow only X2, that means your cutoff frequency the lower cutoff frequency should be between 100 and 300, and the upper cutoff frequency should be between 600 and 800 Hertz. Okay. So the lower cutoff you choose, as we said, between 100 and 300 Hertz. So that is 250 Hertz. Remember, it's a band pass filter that you are building. So it will have a lower cutoff frequency and a upper cutoff frequency. So FC2 is beyond 600 and below 800. So let's choose 650 Hertz. In that case, the coefficient B is obtained by, again, FIR1, 100, this is the order of the filter, lower cutoff, higher cutoff, and band pass. This is the parameter passed to this FIR1, which tells it that it has to calculate the coefficients for the band pass filter. Okay, that is if you want to extract the mid-band signal. And WN1, which is the normalized frequency, so that is 2FC1 by Fs. So 200 and 250, that is 500 by Fs. And WN2 is 2FC2, so that is 1300 by Fs. Okay. Finally, if you want to extract the high frequency band, then how do you choose the cutoff? So look at X2 and X3. So you want to reject frequencies below 800. So you should have a cutoff frequency which is lying somewhere between 600 and 800 Hertz. So let us choose it to be 750 Hertz. In that case, your normalized cutoff frequency is 2FH by Fs. So this is equal to 2 into 750, that is 1500 divided by Fs. All right. So with those basics out of the way, let us now write the program. So this is as usual, you clear everything. Then our F max, remember, is 1000, F minimum is 50. So we define time period for the F minimum. The reason is we are going to display certain number of cycles for the lowest frequency component, suppose 4, 5, whatever. And all other components, of course, will have more number of cycles. So we calculate T equal to 1 by F minimum. Calculate Fs as 10 times F max. So F max is 1000, so this will be 10,000. And Ts, which is the sampling time period, that will be reciprocal of the sampling frequency. So that is 1 by Fs. Then you generate your time vector. So 0, Ts and 4 times T. So what this means is that the signal which has the minimum frequency, it's 4 cycles you will see. Of course, for higher frequencies, more number of cycles will be seen. But you have to select some time, and we are selecting this. Although you could change this as per your convenience. Okay. Now we generate x1, so that is the summation of two sine components, one at 50 Hertz and the other at 100 Hertz. So this is 2 times f min. Then x2 is between 300 and 600. So this is x2, straightforward, 2 pi ft plus 2 pi, 2 sine of 2 pi, 2 times ft. x3 is between 800 and 1000 Hertz. So you generate x3. And finally you generate x by summing all x1, x2 and x3. Now what you do? You define all the cutoff frequencies. Obviously, at a time we are going to use only one filter, either low pass filter or band pass filter or high pass filter. But what we are doing is we are defining the cutoff frequencies for all the filters first, so that we can select whichever one we want to use. So as we have already seen, for the WN1 and WN2, for the band pass filter, this is 500 by Fs and WN2 is 1300 by Fs. The cutoff frequency for the low pass filter we have already studied is 300 by Fs, and cutoff frequency for the high pass filter is 1500 divided by Fs. So it is obvious that at one time we are going to use only one filter. So we will be using either this combination or this cutoff or this cutoff. So what I have done, you can of course write a better program using case statements, etc. But in order to demonstrate, I have simply written two statements for the three statements for B coefficients, and two of them I have just put in comments. So depending on which is not in put comments, which is not put in comments, that particular coefficient will be calculated. So right now here I have kept the band pass filter active, so the coefficients B will correspond to the band pass action. But if you want to show the high pass action, then you can make this active, put the percentage sign in front of this, so you will be calculating the coefficients for the high pass filter. So you choose one of these by appropriating. So as I said, appropriately selecting any of these statements. But as I said, you can write a better program by using case statements, etc. So user can specify whether it is high pass, low pass or band pass. Anyway, so this is the way it is done in order to demonstrate. Then A equal to 1, as we said, this is the FIR filter design, so our A is equal to 1. This is where the filtering takes place. So Y is equal to filter B coefficients, which are calculated from here, A that is set to 1 and X that is the input here. So now we are ready to plot everything. So first we plot X1, and the other statements are required to complete the graph, which we have already discussed often. So I'm not going into the details of that. You can just read this easily. So you plot X1 here. Similarly, you can plot X2, then you can plot X3, and finally you can plot X. So all inputs are plotted here, X1, X2, X3 separately, and the sum is also plotted. And then finally you plot the filtered signal, that is your plot Ty. That is what you do. All right. So let me demonstrate the output to you for all the three cases, low pass, band pass and a high pass. So of course you will have to run the program 3 times by selecting the appropriate statement for the coefficients. So since that is easy to do, I will directly show you the result for all the 3 cases. All right. So first of all, let us see the case in which mid frequency band goes to the output. So all the signals you are seeing here, low frequency signal, as you can see easily here, this is the mid frequency signal, and this is the high frequency signal. This is the lowest frequency, the mid frequency, high frequency, and combination of this. So this signal contains all the 3 bands, and when you filter this, In this particular case, we use coefficients for the band pass. So it's the mid frequency band that goes to the output. Remember, this is low frequency, this is mid frequency. So the filtered signal should correspond to the mid frequency band, and that is what it is. Compare this with this, you will find that they are identical. Of course, for every filter there will be some delay and some transient, so that will always occur at the start. But in steady state, you will find that this mid frequency signal, that is the mid frequency part of the input signal, is identical to the filtered signal. Okay, then let us show the other case where the high frequency signal goes to the output. Again, low frequency, mid frequency, high frequency, the sum. Now look at the filtered signal, and if you carefully look at the waveform here, you will see it is same as the filtered signal. So it is the high frequency signal which goes to the output. Finally, the low frequency signal goes to the output by choosing appropriate coefficients. So low frequency, mid frequency, high frequency combined, and the filtered signal extracts the low frequency signal. So this demonstrates to you how by using an appropriate filter you can choose the low frequency band to go to the output, you can choose mid frequency band to go to the output, and you can choose high frequency band to go to the output. So in this session we have introduced the filter function, and in order to see the application of this filter function, we have solved a problem through a program and demonstrated it. And that's all in this session.